Okay, now it's okay. You fixed it, whatever you did.
Just plugged it in.
I don't know what you do, Jacob, half the time, but it works. Thank you. Okay. So we have 25 rho over 8 would be the mass of this lamina of constant density rho. Okay. You have x squared over 8, but then you integrated it again. What? Oh, maybe. All right, you have 25h. You have that for the mass. All right, let's do the moment from the x-axis. Moment from the x-axis. We said what we would do is take the midpoint right here, okay? Because we need a mass times a distance for the moment from the x-axis. A moment is a mass times distance. Okay? We need the distance, and we said we take the midpoint of this rectangle. Well, the midpoint of that rectangle is the x over 4 divided by 2. So it's x over 8. That's the midpoint. If this function were not 0, we would add the two functions and divide by 2. Okay? That's how you find the midpoint. So 0 to 5, x squared over 32. Take the 32 out, get x cubed over 3 from 0 to 5. You got rho over 96 times a 125. 3 cubed and 0 gives a 0. So you get 125 rho over 96. And I don't see what you have there. Looks like you didn't, I don't know, it didn't look, I don't know. Moment from the y-axis is rho 0 to 5. The distance from the y-axis is x, so it's x over 4 times x this time. So we get rho 0 to 5, x squared over 4. All right, integrated x cubed over 12. So we get rho over 12. We have an x cubed. Okay. And that's a 125. So 125 rho over 12. All right, those are all our ingredients. X bar, y bar is equal to moment from the y-axis, 125 rho over 12 divided by the mass, 25 rho over 8, y bar, moment from the x-axis. Wait, yes, moment from the x-axis, 125 rho over 96 divided by the mass, 25 rho over 8. I don't know, let's simplify this thing. The rows cancel. This becomes 8 over 25. 25 goes in there 5 times 2, because 4 goes over 3. This is 10 thirds. Okay, this simplifies to 10 thirds. Hopefully somebody's checking it out. Rows cancel here. This will be 8 over 25. 25 goes in there 5. 8 goes in there once, and 8 goes in there like 12. Seems to me I get 10 thirds, 5 twelfths for my answer. Okay. 10 thirds, 3 1/3, 5 twelfths. I don't know, it looks pretty good. That looks about right. That's it. Okay, any others? Okay. Rabin, how you doing? Okay, what's up? Well, here's your paper. All right, I'm going to go on then, all right? I'm going on. We're moving on. Let's move on. Here we go. Today is the 21st. Let's talk about alternating series, okay? Up till now, we've been talking about series with positive terms only, okay? All our series have had positive terms. The tests that we have so far, we have an nth term divergence test, meaning what? If you have a series and the nth term is not going to go to 0 as n goes to infinity, you know that series will diverge. That's the nth term divergence test, okay? If the nth term does go to 0 as n goes to infinity, the series may or may not converge. It has to get to 0 quickly enough to cause the series to converge. But if that nth term is not going to go to 0, forget it. The series will diverge. Then we had some comparison tests, all right? We had geometric series and telescoping series where we could actually find the sum. And then we had some comparison tests. Direct comparison, if we have two series, and if the bigger series is known to converge, the smaller series has to converge. And if we have two series and the smaller series diverges, the bigger series will diverge. That's a direct comparison. We also have a limit comparison. You have two series, one's known, one's unknown. Form the ratio of their nth terms. If that limit exists, is greater than 0, and is finite, the two series will converge or diverge together. It's that limit comparison test that gives us that shortcut for difference in degrees as a way of determining whether a series converges or not by looking at the series, looking at the difference in degrees. So that limit comparison test enabled us to take a series like this, enables us to take a series like this, and let's say we have n cubed plus 7. And what can we determine from this series? Does it converge or diverge? Converges, out of way. Because the difference in the degrees is 2. As long as the difference in degrees, denominator minus numerator, is greater than 1, it will converge. Otherwise, it will diverge. It's the difference in degrees. So you can do tons of series. And they don't even have to be polynomials to use that. Fractional things will work too, even though they're not polynomials. If you have something like n to the 3/2 plus 1, and this is the square root of n or something like this, does this series converge or diverge? What is it? Oh. What does it do? Diverges. Out of way. It diverges because the difference in degrees is exactly 1. If the difference in degrees is 1, it will diverge. Okay? If you had to prove it, you would use a limit comparison test with the diverging harmonic series 1 over n. That series will diverge. Okay, so we had the comparison test and we had an integral test. Okay, you take the series, you take the integral. If the integral converges, the series converges. If the integral diverges, the series diverges. Okay? So we did that. And that led to P series, which is basically this thing here. I think that's what we did so far. Okay? So I'm going to go on from here. You ready? Let's take a look at an alternating series. Okay, what is an alternating series? It's a series that has this form. Or this form. Where all the a sub i's, okay, these here, are positive terms, where the a sub i's are positive. These a sub n's are positive. Okay? So what gives it, the alternating is the negative 1 in front. We'll go negative 1, positive 1, negative 1, positive 1, or it'll go positive 1, negative 1, positive 1, negative 1. For example, let's take a look at this. This is an alternating series. When n is 1, we get negative 1 to the 1 plus 1. Negative 1 squared is 1. We get 1 over 1 plus. When n is 2, we get 2 plus 1, 3. Negative 1 cubed is negative 1. So it's a negative. Plus. Now when it's 3, this becomes 4. That becomes a positive 1. Okay? Then a negative 1. This is an alternating series. It alternates plus, minus, positive, negative. Or it could go negative, positive. This series has a name, okay? It's TED. No, it's an alternating series, okay? It is an alternating series. It's called the alternating harmonic. Okay? The alternating harmonic. Now, there's a test to determine whether alternating series converges or diverges. And here's the alternating series test. It goes like this. Given alternating series, this is either n or n plus 1. I don't really want to write it twice, okay? I'll write it twice. Okay? Given that series. Then, the series converges if two things must happen. The terms must not be increasing ever. Okay? A sub 1 is greater than or equal to A sub 2, which is greater than or equal to A sub 3, etc. That's the first condition. The terms can never be increasing. Okay? Second, the limit as n goes to infinity of A sub n must be 0. So as long as you've got the terms not increasing, okay, and the nth term is going to go to 0, that alternating series will converge. It makes sense because when you add and then subtract, okay, instead of going off to infinity, that process of subtracting every other term is going to keep the thing restricted to around 0. And that's what happens. So the conditions for an alternating series to converge are pretty lax, okay? Let's do one. Oh, let's do this one. Does the alternating harmonic converge? Everybody got this all right? Who else?
There's nothing under that? No, number 2?
There's what?
Is there anything under number 2?
No. That's it, number 2. 1, 2, done. So, let's take a look at the alternating harmonic. Here's the alternating harmonic. Our series, call it S. 1 minus a half plus a third minus 1/4 plus a fifth. So, let's look at the terms. Is it the case that 1 is greater than or equal to 1/2, which is greater than or equal to 1/3, which is greater than or equal to 1/4, etc.? Is that true for all the terms?
Yeah.
Yes, it is. Is everybody okay? Everybody's okay? Is it too hot in here?
I think it's a full moon.
It's a full moon? You think that's what it is?
Always makes people act weird.
Makes you what?
No, it always makes people act weird.
Really? Yeah, but I don't think you need a full moon, though, do you? All right. This is certainly true. These terms are decreasing all the time. They're never increasing. Is it the case that the limit, as n goes to infinity, of the nth term, that A sub n, not the negative 1 part, just the A sub n, which is 1 over n, okay? What's that limit as n goes to infinity? 0. Done. Series converges. Okay? That's it. It's a simple test for convergence of an alternating series. And what we're going to use on the last class We want to get an approximation as to what that sum is of an alternating series. We may not be able to get it out exactly like we can with telescoping sums and geometric ones, but we can at least get an approximation. We know this thing converges to something. We can get an approximation by doing this. This sum is approximately equal to, let's take the first 4 terms to approximate the sum of this series. This sum of these first 4 terms, let's go to 12. 12 minus 6 plus 4 minus 3. That's equal to, what, 3/4 or something? 6, 10, no, 6, 10, 7 twelfths. How good an approximation is that to the actual sum? Well, I'll tell you. The error in using this for an approximation is less than or equal to the next term. Okay? Is less than 1/5. Okay? And that should make some sense, okay? Because if you use this to approximate the sum, add 1/5, but then you have to subtract 1/6. So you're adding something less than 1/5 onto it, okay? So the error is less than or equal to 1/5. We're going to use that on our last class, okay? The fact that we can do an approximation for the sum with these alternating series by using the next term as our error. And that's what the error is, okay? All right, but there's more with alternating series, okay? Because with this alternating series, what about its positive series? Let's take a look at the positive series. Let's take a look at, call this S sub 1. Let's take a look at S sub 2, its positive series, the alternating series. Okay. Let's look at its positive series, the harmonic series. What do you know about this harmonic series? Does it converge or diverge? I didn't quite hear that, Jimmy.
Converge.
Diverge. That's what I thought. That's what you said. This is it here. This is the harmonic, okay? 1 over n, what's the difference in degrees? 1. That diverges. An integral test, the improper integral from 1 to infinity of 1 over x, diverges, okay? Diverges. Okay, so here's what we have. We have an alternating series. It converges. We just did it here. Its positive series diverges. That makes the alternating series conditionally convergent. Or you could say converges conditionally. Okay? Why the word conditionally in there? Because it depends on the series alternating in order to converge. If that series did not alternate, if it did not go plus, minus, plus, minus, plus, minus, it would diverge. It would be this harmonic and diverge. But because it goes plus, minus, plus, minus, plus, minus, we prove that it does converge. It converges conditionally. Condition, what is the condition? That it alternates. Because if it didn't alternate, it wouldn't converge. Okay? Alternating series have 3 possibilities for converging. They can converge conditionally, which is what we have here. They can converge absolutely. All right, this is why I saved this to after evaluations. I do this lecture. Make sure you do the evaluations first, because after this lecture you'll hate me. So that's the way it is. Okay. So what are the three possibilities? Here are the three possibilities for alternating series. And I'm going to tell you this. On the test for this chapter, guess what? There will be 3 alternating series questions. And perhaps it's a coincidence that there are 3 possibilities for alternating series, okay? It could be a coincidence. It could be that on the test, 2 of them are conditionally convergent and the other one is absolutely convergent. That's possible. I'm just going to throw that out there. Here are the 3 possibilities. 1, conditional convergence. When you get conditional convergence, you get that when the positive series diverges. Did you read that? Oh, gee, whoa, whoa. Okay. And the alternating series converges. This is what we just had, okay? Okay. What else can happen? You get absolute convergence, or converges absolutely. Okay. Absolute convergence. What happens here? This is when the positive series converges. Let me tell you, if the positive series converges, you don't have to test the alternating series. It's guaranteed to converge, okay? By a direct comparison test, in effect, because it's smaller than the positive series. It goes, the terms are plus, minus, plus, minus. Instead of adding all positive terms, you're adding and subtracting. So it's going to be less than that positive series. So if the positive series converges, you're done. We got absolute convergence, okay? Let me give you an example of such a thing.
But there is going to be one more of those?
Yeah, there's one more. Should I put that here? I'll put it here. I'll do it now. Should I do it now?
I just need to leave room in there.
Oh, you need to leave room. Okay. All right, I was going to do an example over here. Here we go. Here's an example of, there's one more. Okay? Here's an I want to give you an example of this stuff. Let's do an example. For example, let's do this one. Here's an alternating series. It goes like this. 1 minus 1 over 2 squared. Okay? Second term, 1/4, plus 1 over 9 minus 1 over 16 plus, etc. Okay? That's the alternating series. Okay? That's the alternating series. Now, does it converge absolutely? Well, how do you tell if it converges absolutely? You test its positive series. What about this series, 1 over n squared? Does it converge or diverge? 1 over n squared. It converges.
Is that one conditionally convergent?
Which one?
The number 2 one we just...
No. It's absolute convergence. Okay? Why? Because its positive series converged. That makes the alternating series converge absolutely, or absolute convergence. Its positive series converges. Okay? You better ask me quiet. I don't know. I see a lot of doubt out there. Lewis.
We can pretty much see if it converges or not from the degree, right?
Yeah, that'll do it. It's a p series, or p is 2. Difference in degrees is 2, so you know it converges. If the positive series converges, that alternating series converges absolutely.
So on the test, you're going to give us that, or are you just going to give us a series and say if it converges? like, are you just gonna write 1 minus 1 over 4? Or are you gonna give us?
Would it make a difference to you?
It would.
It would? You couldn't take this and write this?
No, I know where you're getting it from, but I'm like confused as to why is the numerator always 1? When you're plugging in 2 for the, like, if you plug in 2 for n,
Yeah.
shouldn't it be?
Well, what's negative 1 cubed?
Cubed. Oh,
Negative 1 cubed is negative 1. Then it will go positive 1, negative 1, positive 1.
gotcha.
Okay? I'm going to tell you right now, I think I give them to you in this form. Okay? Yes?
I just want to see a positive series that converges.
That converges.
Yeah.
There you go.
Right, is there one that, can you write that out?
I did. This converges.
Like,
What are you saying?
Like the same way that you read the alternating. Like 1 plus blank plus blank plus blank plus.
This one here?
Yeah, how would that expand?
1 plus 1/4 plus 1/9 plus 1/16, etc.
All right.
Okay. You got one more. Number 3. Divergence. What could happen? The alternating series may diverge. For example, what do we have? What kind of an alternating series would diverge? Well, let's take a look. Let's take a look at this one. Here's an alternating series. Let's see, let's write out a few terms. We have 1 over 2 1/2 minus, this with the negative 1 will alternate, 2/3 plus 3/4 minus 4/5 plus, etc. It's an alternating series. Does that alternating series converge or diverge? It diverges. Why? How do you know it diverges?
You wrote an example.
That's correct. That is a good point. I wrote it under the diverging thing. I can't argue with it. That's using your brains, okay?
2/3 is greater than 1/2.
Yeah, there's a good call. It fails the alternating series test for convergence because the terms are not getting smaller. The positive terms are getting bigger. The bottom line is the limit as n goes to infinity of this n over n plus 1. What is that limit equal to?
Infinity?
No. 1. It's not 0. If that limit is not 0, that series will diverge. There's no question about it. It doesn't matter if it's a positive series or an alternating series. In order for any series to have a chance at converging, at having a finite sum, the nth term must be going to 0. If they don't go to 0, if that nth term is not going to go to 0, forget it. It's no way is it going to converge. It will diverge. Yes, Libby. Abby.
If the alternating series diverges, does that mean it's positive also?
Absolutely right. Yes.
Yes.
You wouldn't even have to test it. Yes. But that wouldn't even be a question. Okay?
But this is only for alternating series.
Yeah, these 3 things are for alternating series. An alternating series can have conditional convergence as long as it converges, but its positive series diverges. It could converge absolutely if its positive series converged, okay? And it could actually diverge if it fails the alternating series test for convergence. The thing you always use on this, that's the nth term going to 0. If it's not going to go to 0, then forget it. It will diverge.
So is the only one that you can't have a positive series that converges and then an alternate series that diverges? That's not possible.
That is not possible. That is impossible. Okay. Okay, you ready? That's alternating series. Maybe I better give you one. Here, do this one. You guys do one. Let us see. What about this? You tell me, this alternating series here. Okay, check it out. Look at it. It's one of three things are going to be true. One of three. Either this alternating series will have conditional convergence, absolute convergence, or it will diverge. Okay. Okay, how we doing? I need one super bright student to answer that question. So, give me a minute. I'm going to go next door. No. Just kidding. Who's got an answer here? Go ahead. Sam, how you doing? Oh, see, now we get the super bright student coming in. All right, we need it. We need you. We need your brain.
Okay.
Okay.
I got a bit of divergence.
I want, diverges. Okay, he says diverges, okay? We got some other, okay, you got some reasons for
The
that?
value of the second term, or I'm sorry, the value of the third term is greater than the second term?
Is it 1 over the square root of 3 is greater than 1 over the square root of 2?
Oh, wait, no. It's not, so
It's
that's actually
not.
not right.
Shoot.
But it thought it diverged
Okay, you thought it diverged.
for the wrong reason.
So it may still diverge, we're not sure.
Yeah, I got it.
Okay, that's okay. You gave it a shot.
Conditional.
Conditional convergence, says Jim. Anybody want to disagree with Jim? Anybody foolish enough to, oh wait, Jim is foolish enough to disagree with
The
Jim.
positive converges, and then
You saying the positive if the positive converges, you're done. There's nothing more to do because you got absolute convergence. You don't even have to do anything else. Okay, go ahead.
so it's conditional.
Oh, it is conditional. You're back to
Sticking
conditional.
with it, yeah.
Okay. Anybody wish to disagree with Jim? Except for Jim disagreeing with Jim. Anybody else wishes to disagree with Jim? I can see it. Some people are thinking. Abby's thinking about disagreeing. No, you don't disagree. Anybody else? Karen?
Agree.
You agree?
I agree.
Okay.
I'm going with the conditional.
That's what he is. Okay, so you agree as well. Well, let's check it out. Let's see if he is correct. What do you do here? Well, here's what you do. The first thing to do is look at the positive series. Because if the positive series converges, we're done. There's nothing more to do. It's absolutely convergent. So you look at the positive series. What about that positive series? Does it converge or diverge? It diverges because the difference in degrees is only 1/2. Not good enough. So this diverges. That rules out absolute convergence. That's out of the question now. We either got conditional convergence or we have divergence. The next thing to do now is to test to see if it passes the alternating series test. If it passes that, we got conditional convergence. If it fails that, we have divergence. Now, let's look at the terms. Okay, first term, this is, okay, 1, is that greater than or equal to 1 over the square root of 2? Is that greater than or equal to 1 over the square root of 3? Greater than or equal to 1 over the square root of 4, etc. Are the terms decreasing here? Yeah, they are, because the square roots are getting bigger, the fractions are getting smaller, that's true. Is the limit of the nth term 0? Is that 0? Yes, it is. Okay, it is 0. Therefore, the alternating series converges. But since it's positive series diverge, we have conditional convergence. Yes?
What happens if the difference in degrees 1 again? Is it
Diverge. Diverge. Difference in degrees is 1. It diverges. On the positive series, that's a diverging, it's called the harmonic series, it diverges.
We're not gonna get like a cheat sheet of all these crazy rules we have to remember.
I have no control. If you want to write under your tongue and then kind of read under your tongue somehow during the test, that's your prerogative.
No, I just felt like if you had like a printout, like a short list of all these things we have to.
No, it's going to have to be in your brain.
Awesome.
Your brain, which is way more than sufficient.
Sounds great.
Way more than sufficient. Okay, way more.
I think you could review
Thank you. All right, I have a feeling I better give you another one. I'm going to give you 3 of these on the test. Let me give you another one. Okay, try this one. Oh, all right, I'm going with ends here, yeah. Okay, n equals 1 to infinity, negative 1, n plus 1. And let's go with, oh, okay. Let's go with, how about n? Three possibilities. Okay, how we doing out there? I need one confident person to put forth an answer. Karen.
absolute convergence?
She says it absolutely, too. Absolute convergence, Karen says. Anybody dare to disagree with that confident person? Okay. You won him over. Okay, so he is with you. Anybody else? Nobody else. Abby, what? Are you daring to? Ha. All right, go ahead. What do you say? She says diver. That's the opposite end of the spectrum, for Pete's sake.
I think so. That's what I got.
Oh, now everybody chimes in. Once you have one person disagree, then the rest of you guys agree with the disagreeer. Let's take a look. Let's see.
Yeah, now that I think about it.
All right, let's take a look. What do you do here? What you do is look at the positive series first. Here's the positive series. Whoa, here's the positive series. What the heck? That positive series diverges for sure. That goes right off to infinity, the sum. What we have just done is ruled out absolute convergence. What we have to check for is conditional convergence or divergence. How do you check for it? Well, let's look at the terms, okay? We have 1. Is that greater than 2? Is that greater than or equal to 3? No, the terms are not decreasing. They're increasing, for Pete's sake. Okay? This is not true. Therefore, diverges. Okay? Diverges.
Can I have the notes?
When we do the alternating series test, we're ignoring signs, right?
Say what again?
When we do the alternating series test, we're ignoring signs.
Yes, you're ignoring the negative one. You look at the terms, the a sub i's, the positive terms, and if they are decreasing, then you look at the a sub n and see what happens as n goes to infinity. So this is a diverging series. Those terms are not going to zero. They're increasing, actually. It diverges. All right, one more. I'll just do this.
What were we doing with density?
What's that?
These are homework problems, right?
Yeah, that was from ages ago.
Okay.
Yeah, some student was way back there, so I won't say any names. Some slacker was slacking mightily. Okay, it was way back. So we did that. Where's Brendan? Oh, man. Maybe he's pitching tonight. Maybe. Maybe he's doing better than David Price did for the Red Sox today. It wouldn't be difficult. But anyhow. All right, I need one confident student to give me an answer. So who do we have?
Absolute convergence.
Absolute convergence. Let's do it. Anybody want to disagree with him, first of all?
Conditional?
Conditional. Anybody else? Want to get on the record. Let's check it out. What do? You check out its positive series first. What about that series? Does it converge or diverge, that positive series? It converges. We are done. We have absolute convergence. Converges absolutely. Difference in degrees, 5, more than enough to have it converge. Okay? We understand. Here it is, P series. Let me just do this again. Okay. These are P series. What do you get for P series? If P is greater than 1, that series will converge. If P is less than or equal to 1, it will diverge. Okay? Those are P series. You can prove them with an integral test. Okay? All right, I'm going to go on. You ready? We have a couple more tests. We have the ratio test. Given series. Now, they can alternate or not. It doesn't even matter, okay? You can have a series like this, or there must be a better way of denoting it. Could be either one. You know what I mean? All it means is one starts out with positive 1 and then goes positive, negative, positive, negative. And the other starts out negative 1, negative, positive, negative, positive. It doesn't matter. Then, let L be the limit as n goes to infinity of the absolute value of the n plus first term over the nth term. Okay? We're going to take the limit of the n plus first term over the nth term. We're going to take the absolute value. What that does is takes out the negative 1 part. Okay? Takes out the negative 1 part. When, in effect, what we're doing is testing its positive series. Okay? Okay? If we have three possibilities for L. If L is greater than 0 and less than 1, then the series converges absolutely. After all, we tested its positive series, and if it passes this condition, then it converges absolutely. If L is greater than 1, the series diverges. If L equals 1, the test fails. Oh my. The test is inconclusive, and you have to try something else. Okay? Now, when do we use ratio tests? I will tell you. Is everybody okay with this? Okay.
Wait, what's this test fails? Is that what? Oh.
You have to do something else. The test is inconclusive.
The alternating series.
If it's an alternating series that you're testing, yeah, you may want to try something like that, an alternating series test. You may want to try something else, an integral test, something else. This test fails. Okay. This test just doesn't cut it. It just doesn't work. You have to do something else. When do you use this test? Well, I'm going to show you. You ready? Okay, I'm going on. Well, I'm trying to give Sammy a chance to kind of catch up here.
Gracias.
What's that?
Gracias.
Okay. I'm going kind of slow here. I'm risking people nodding off here. You're not nodding off, are you, Caroline? No. Wait a second. Some people are on the verge of nodding off.
You don't have to wait. I can just look at the video after.
Yeah, that's true.
Yeah.
Okay. All right. Let's take a look at this series. N factorial over e to the n. We haven't dealt much with factorials. The very beginning of this chapter, I mentioned factorials. And you may have had some in your sequences in the beginning of the chapter, but we haven't done much. And the reason is our test so far didn't really work for factorials. An integral test, forget it. You're not going to take the integral of a factorial. It's a discrete function. It's not continuous. And you're not going to take its integral. Difference in degrees. Factorials don't have degree. We're not polynomials here, okay? So we need something different. The ratio test will take care of this. But I'm also going to give you your second shortcut, okay, from this test. But right now, let's use the ratio test on this. Let's take the limit. This could be equal to 0, okay? Greater than or equal to 0, less than 1, okay? Because it just dawned on me this is probably going to be 0. No, it's not. It's going to be the other way. But it could be equal to 0. The series converges absolutely, okay? Could be equal to 0. Okay, you ready? Let's do it. Take the limit as n goes to infinity. Absolute value, well, there's no need for absolute value. We don't have a negative in here. Let's take the n plus first term. Okay. Over the nth term. And we want to find the limit as n goes to infinity. Okay? Whoa. Here we go. This is going to be nasty. That's the limit as n goes to infinity. N plus 1 factorial. This e to the n comes up there. The n factorial here is here. The e to the n plus 1 is here. Okay? Now, we're coming to simplify. What's n plus 1 factorial over n factorial? You guys know that? Maybe not. Here's what it is. Let me do this. I could drop the absolute value symbols here too. N plus 1 factorial is n plus 1 times n factorial. Okay? 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what 7 factorial is. 7 factorial is 7 times 6 factorial. N plus 1 factorial is n plus 1 times n minus 1 times n minus 2, dot, 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 3 times 2 times 1. N plus 1 factorial is n plus 1 times n factorial. Okay? Okay? E to the n over n factorial e to the n plus 1. Now, let's simplify. N factorials cancel. I have an n plus 1. What's e to the n over e to the n plus 1? E. The e is down here. Okay, subtract the exponents. What's the limit of n plus 1 over e as n goes to infinity? Yes, it is. It increases without. E is stuck at 2.71828184590452356 whatever it is at the end there. But n is increasing. Okay? This goes to infinity. What does that tell you about the series? Since this is going to infinity, okay, which is where? Okay. Which is greater than 1, the series will diverge. Okay? It diverges. Okay? Therefore diverges. Okay, here's the deal. This is a question as to who is increasing faster. Are the factorials increasing faster than the exponential function or not? What we've just shown is that this ratio of the n plus first term to the nth term is going to infinity. It's increasing. That says that the factorials are increasing faster than this exponential term. Okay? If I did this series, that ratio test limit would be equal to 0, and that would show that it converges. Okay? Converges. Because the factorials increase faster than exponential functions. Okay? So I'm going to give you a list of relative rates of increase of functions. And you can use this list to determine whether series will converge or diverge in many, many cases, just by knowing how fast these things are increasing. You could prove them with a ratio test, but you can look at them and say it converges or diverges because of their rate of increase. Now here we go. The slowest of all of them are the natural logs. Okay? You've got natural log functions.
So they're not like a handout list, it's like a you have to remember it list.
You have to remember it list.
Get towards the end, it's coming up short.
No, you don't. That's not true.
If that n plus 1, you know how you got the n plus 1 times n factorial?
Yes.
If it was like, let's say, n plus 5, what would the side be?
If I had n plus 5 factorial there,
Yeah,
and I had an n factorial down below,
yeah.
it would be n plus 5, n plus 4, n plus 3, n plus 2, n plus 1, n factorial.
And then the n factorials
Would cancel out, yes.
So that would come to the denominator, all those, what you just said?
No, they would stay up
All that
here.
would stay there?
Yes.
Okay.
All right, you have natural log functions. They're the slowest increasing functions of all. Okay? Then you have polynomials. Okay? Okay? These are things like n cubed and n to the 10th. Things like that, where the base is the variable and you have a constant exponent. Then you have exponential forms, 10 to the n, exponential forms. They have to, the base has to be greater than 1, though. If they're not greater than 1, exponential forms actually decrease. Okay? Then you have factorials. Then you have, finally, the fastest increasing functions of all that we will be dealing with occasionally. You may have one example somewhere. N to the nth terms. Okay? N to the nth increase faster than all of these. Okay? So, here you go. You ready? Let's do some examples. Let's take a look at this series. Let's take a look at natural log of n over n cubed. What can you tell me about natural log of n over n cubed? It converges. And the reason it converges is because the n cubed, a polynomial, increases faster than the natural log function. Okay? Converges.
So the denominator is increasing faster than the numerator converges.
Correct. As long as it's increasing, and these give you the relative rates of increase, so this is increasing much faster than this, so it will converge. Okay? Just converges. Let's do this. Let's suppose you have 2 to the n over n to the 5th plus 1. Converge or diverge? This diverges because the numerator is increasing faster. It may not be faster in the beginning because 2 to the n just doubles and this goes to a 5th power. But you know what? Sooner or later, exponential functions catch up to and surpass polynomials. I don't know, sometime it will. We need.
The next one.
Oh, okay. I don't know. We could run out. We could do a couple of these guys and see when it starts catching up. If you take 1, you get 2 over 2. 2, you're going to get 4 over 33. Whoa, this guy's increasing way faster. 3, you're going to get 8. Oh, wow. 3 to the 5th, I don't know what the heck, 729? Is that about right? So you get 730. What is it? Oh, is that it? Oops, I went too far. Okay, 243, 244. And then this is going to be 16. And this is going to be 4 to the 5th, whatever the heck that is.
25,
What is it?
1025
Wow.
with the plus
We
one.
gotta go a ways here. All right, then you got 32, and then you got, I'll tell you what, it's going to take us a while, a lot longer than I thought. But sooner or later, the exponential will catch up to and surpass the polynomial. You're going to have to trust me on this. No, you don't have to trust me on this. We could prove it. We could prove it with a ratio test. Let's do it. Let's prove it with a, what? You want to do it? No, you don't.
You get
I
there
like
somewhere,
What's that?
somewhere between 25 and 30.
Oh, you can do that on there? 25 and 30. We got to go out 30 terms before it starts catching up. It will catch up and surpass it. Okay? I'm going to prove it. What the heck? We should prove it. Let's do it. The heck? Here we go. Here's what we're going to do. We're going to use the ratio test on this. Let's take the limit. N goes to infinity. Nth plus first term over the nth term. Okay? That's equal to the limit as n goes to infinity. 2 to the n plus 1 You got n to the 5th plus 1 over 2 to the n, and you got an n plus 1 to the 5th plus 1. Okay? Okay. Let's take it a little, oh, and we can simplify. 2 to the n plus 1 over 2 to the n. That gives us a 2. We got n to the 5th plus 1. And if you multiply this out, well, I'm going to have to do it. All right, I'm going to multiply this out. It's n to the 5th plus 5, n to the 4th plus 10n cubed plus 5n squared plus 1 plus, did I do enough? 1, 5, 10, 10 I need. 1, 5, 10, 10, 5, and then a 1 plus 1 is 2. Okay? When I multiply this out, this is what happens. I get this. What's this limit now is n goes to infinity? Forget the 2. What's the limit of n to the 5th plus 1 over n to the 5th plus all this other stuff? What's that limit equal to?
Is it n to the n factorial?
No. What's the limit of n? It's 1. Okay? It's 1. Same degree. Ratio of leading coefficients is 1. Use L'Hopital's if you want. L'Hopital's will give you the same answer of 1. What? This 10 here? That's a 10. Okay. All this other stuff doesn't really matter. The fact of the matter is you got an n to the 5th over n to the 5th. Same degree, Pauline. Oh, I have looks of doubt out there. What's that? It's 1 without the 2. With the 2, we get 2. And because it's 2, it diverges. Okay?
Wait, so it is 2.
Yeah. This part of it's 1 times the 2. Oh, that was that look of doubt? Okay, good. Okay? So it diverges. What does that prove? Well, that proves that the 2 to the n does indeed increase faster than the n to the 5th plus 1. Because if it didn't, these terms would be going to 0 and it would converge. If it went to 0 fast enough anyways. Oh, okay? Now here's the problem. Okay, what I gave you works for lots and lots of series. Virtually all the series that you get for homework, you can look at them and just say they converge or diverge just by using one of two things: difference in degrees or relative rates of increase. But there are some problem series, okay? Let me give you an example of a problem series. Let's suppose we have 10 to the n, n factorial, over, something here. Oh, I hate to do this to you guys, but let's do n to the n. This is nasty. Now, here's the deal. I told you that n to the n increases faster than all the other ones, which it does. However, in this one, we have an exponential times a factorial. That product is going to increase pretty fast. Is it fast enough to catch up to the n to the n? That's a question mark. We don't know. It's when you get these combinations in here that you have a problem. Okay? So, how do you do a problem like this? You do a ratio test. So let's do it. N plus first term divided by the nth term. Okay? You with it? Oh boy, I can see that. Oh man, I killed you all. Well, I still got a little ways to go tonight too. Oh boy. Oh boy, this is gonna be nasty. All right.
Still another section of it?
Yeah, well, we have root test, but that's pretty simple. And then we have power series, though. That's going to take 2 hours at least. All right, so we have 10 to the n plus 1, an n plus 1 factorial, This n to the n comes up here. Down here, we have a 10 to the n. We have an n factorial. And we have an n plus 1 to the n plus 1. Okay. So, well, what can we do to simplify? We have a 10 to the n plus 1 over 10 to the n. What does that simplify to? Just subtract the exponents. We have an n plus 1 factorial over n factorial. What does that simplify to?
N plus 1.
Thank you. It certainly does. Very nice. Because n plus 1 factorial, like we said before, is n plus 1 factorial times n factorial, and factorials cancel. Now, over here we have an n to the n over an n plus 1 to the n plus 1. What happens here? What can we do here to simplify? We have an n plus 1 and an n plus 1 to the n plus 1. What do these simplify to? Oh,
Would it all be over n plus 1 to the n?
perfect. Wow! Nicely done. Because this is to the first power, we have the same basis, subtract the exponents. So now we have a 10 n to the n over n plus 1 to the n. Okay? But they're the same exponent. So we can rewrite this. Okay? Are we okay? Are we all right? Go ahead. Oh, okay. Whee! Okay, how are we doing? Okay. Now, I can combine these. They have the same exponent. I can rewrite this as this. Okay.
Pull it down.
Oops. Okay. All righty. What is this limit equal to here? We have n going to infinity, n over n plus 1 to the nth. It looks like it should be 1. It's not. Okay.
1 to infinity is that, right?
Yeah, 1 to the infinity is an indeterminate form, okay? And this thing is heading towards 1. It's not identically 1. If you had just a 1 there to the nth, as n goes to infinity, that would be 1. But we don't. We have this instead. I'm going to add and subtract 1. Oh, yeah. Am I getting out of order? I probably am.
We're good.
Thanks, Sam. I'm going to add and subtract 1, allowing me to write it this way. 1, n plus 1 over n plus 1, minus 1 over n plus 1 to the nth. Okay. You with me on this? All right. Well, here's the deal. This limit here, believe it or not, okay, is one we've looked at. We've looked at in this form, 1 plus 1 over n to the n as n goes to infinity. And what's this limit equal to? We've done this one. Yes. We've done this one when we were talking about L'Hopital's. We don't have L'Hopital. It's 1 to the infinity, just like this one is. You remember what this one came out to be? No, huh? Okay, fair enough. Here's what we did. We couldn't use L'Hopital's on this, but we did its natural log. That's how you would evaluate this. You take its natural log, you eventually get it into L'Hopital's form. Okay? You don't remember doing this one here? The answer to this, the limit as n goes to infinity, is equal to e. Remember that? No? Wait, was nobody here that night? That class? Everybody was, I was talking to an empty room that night. Oh, yeah. No, we did that. What's that?
Is that what you did on Monday?
Yes, I was here by myself on Monday and did it. Yes, good call.
What happens, we can cover material after 8 o'clock at night, but that doesn't mean anybody retains it.
Yeah, I know. Okay, here's what I'm telling you. This we did a couple weeks ago when we were doing L'Hopital's. Boy, you're all dying on me. Holy mackerel. We were doing L'Hopital's rule, and I said we couldn't use L'Hopital's on this, but what we would do instead is take the natural log of this and see what happens. And eventually, I got it in the right form for L'Hopital's. You may look back at your notes. It's not that long ago when we were doing L'Hopital's, okay, the last chapter, right, L'Hopital's. And we did this, and we proved that it comes out to E, okay? Okay, it does. This here limit comes out to E times 10. The fact of the matter is it's greater than 1, okay? It's greater than 1. That's all we really need to know is that 10 times that is greater than 1. And that means the series diverges. So here's the deal. For almost all of the series that you're going to be doing, you should be able to look at this series and determine whether it converges or diverges by using either difference in degrees or relative rates of increase. The only time you can't do that is when you got combinations of these things. Then you don't know, and you'll have to use a ratio test. However, I will tell you this. On your test, I don't believe you ever have to use the ratio test. I think they're all going to be simple, straightforward ones. Right? We're not after really complicated ones. All right, we have one more test to do, a root test. Okay? If you fail this, then you each have to get a root canal, and then that's not very pleasant. A root test, given some series. Okay. Let L be the limit as n goes to infinity of the nth root of the nth term. Okay. The nth root of the nth term. Okay. Then, if L is greater than 1, series diverges. If L is less than 1, but greater than or equal to 0, the series converges. If L equals 1, what do you think? What's that?
Fails.
Fails. Test fails. You have to do something else. There's one specific kind of series where you use a root test, and that's a series that looks like this. Wow. Yeah. This is pretty silly, but that's the kind of thing it is. Let's take a look at this. The only series you use a root... Yes? Where am I? Oh, I'm off down the bottom down there? Oh, what do you mean? You're looking at the top still? Okay. Yeah, no problem. The only time you use a root test is when you have an exponent hanging out by itself like this. Okay? Why? Because the root test will cancel that n out. So the root test says, okay, what we're going to do is take the limit as n goes to infinity, of the nth root of this nth term. But you know what? What is that nth root? You could rewrite it this way. There's the nth term. The nth root is 1 over n, the exponent. Okay? That's what the nth root is. And what happens to these two? They cancel. That's the only reason for using the root test, is you can use it on a term like that, where the n is out there by itself as an exponent. It will enable you to cancel it. Now, as n goes to infinity, what happens to 2 plus 1 over n? Where does that go as n goes to infinity? I've killed you all. 2. Thank you, Jim. That's equal to 2, because the 1 over n is going to go to 0. That's equal to 2. That's greater than 1. Therefore, the series diverges. Okay? You almost never use a root test. Okay? Okay. Now, I need some feedback here. We could go on to the power series, which will take some time, a half an hour or so. Or leave it for next time, but that makes next time's class a little bit longer than I anticipated. The power series and then the Taylor series, which is a power series, so they are related, so that wouldn't be bad. I need some feedback. What do you guys think?
Next time.
What's that? Next time? What?
Just put it off. Deal with it later.
That's the tendency for people, huh? To put it off.
It'll give us time to work on the in the labs.
And the labs too, yeah, wow.
We'll be fresher
Just
on
on
Monday.
Monday, too.
Also older.
Fresher on Monday and older on Monday and wiser. We're having a discussion of whether we should stop now with the ratio and root test or go on to power series with radius and intervals of convergence.
It's hot in here.
It is hot in here, that's the thing.
Yeah.
That clinches it. With Mr. Yes, sir. All right.
I got you out.
All right, see you Monday. We got the power series and Taylor series on Monday then. You're not going to thank me on Monday.
Yes, I'm
I won't run over you the next time.
Yeah, thank you. Boy, I killed them, Jimmy. Look at them, they're all dead.
I won't be here May 5th for the this final. It's like, should I do that like the day before?
Yeah, sure. We can do it.
Ratio test. Ooh.
Root test, ratio test.
I missed notes.
I haven't done that in
last
years.
week. I don't have them. I just wait and come get them tomorrow. You're my work
The
schedule.
notes from last week, I just gave the video to Devin tonight, the notes from last Thursday. So he's putting them up now. The notes themselves, I probably have on my desk. You want to go, we'll go check it out? Let's go.
I would have to re-download Mathematica because I'm not going to have any problem with like license issues or anything like that.
Wait, say that again now?
I have to re-download Mathematica.
You do?
Yeah. Am I going to have any like, issues like with license or anything? I don't remember exactly the process with that.
You go to the website, the STIC website, and do it. Now, I can't guarantee anything.
All right.
If you have an issue, what you should do is email Carlos Pedro, cpedro@stick.edu, and tell him what the issue is. Okay?
Have a good weekend, Bruce.
And we'll see what happens. We'll see, Chris.
Question.
Yes.
So when you're doing this, right, you have like, when you're doing this, you said, okay, you have like a set of rules. Look at the positive series first.
Yeah.
What was the second rule? Does it pass something test? I forgot what that was. Does it pass?
Does it pass a convergence test? Does the positive series converge?
So does it pass the convergence test?
Yeah. Yes,
Okay. Does it
for the
pass-
positive series, yes. Whew. Wait, oh, I'm still recording.